Our next topic is modulus of rigidity. Let us first remind what is shear strain. We have already discussed shear strain. Let us first some revision of shear strain. What is shear strain? We have already discussed that if there is a block like this and we have applied, suppose this block is A, B, C and D, and we have applied a force on a shear axis or parallel axis of this. So suppose here some force is applied, suppose P, and to this force this side BC will shear off, right? And there will be some change in dimensions of this side like this, right? Like this B becomes B dash, C becomes suppose C dash, and this angle, this is angle phi, this angle is phi. Is it okay? Suppose this length is L and this length is delta L, or this length is delta L. This CC dash, this length or this length, this is delta L. So we have shown that shear strain will be equal to change in length upon original length, that is equal to B dash upon AB, or you can say CC dash upon CD. It is same thing, right? Now shear strain, now in this triangle ABB dash, in triangle ABB dash, you can see it is a right angle triangle. You can write tan phi will be equal to perpendicular upon base, means BB dash upon AB, so that will be equal to delta L upon L. From these two equations we can write shear strain as tan phi equal to delta L upon L, or you can write, because tan phi is nearly equal to phi when there is small angle, for small angles, so you can write phi as delta L upon L. So this is our shear strain. This we have right? So shear strain is delta L upon L. Now what is modulus of rigidity? This at this point we want to come up to this term, what is modulus of rigidity, right? So if this is shear strain, due to this strain, shear stresses will be developed in the material, which is given by tau multiplied by area, that is the shear stress developed in the material, or you can write at shear stress will be equal to load per unit area. This is the shear stress developed in the material, and within elastic limit, this shear stress will be proportional to this shear strain, and when we remove this proportionality sign, we can write that tau will be equal to G. This modulus of rigidity is noted by G phi. Shear stress equal to some constant which is called modulus of rigidity, and strain, shear strain. So G will be equal to shear stress per unit shear strain. So this is the modulus of rigidity. So modulus of rigidity is the ratio of ratio of shear stress to shear strain. Within certain limit. Elastic limit. So this is our modulus of rigidity, and this is the shear strain phi delta L upon L. In this session, we are going to study the stresses on an inclined section at a certain angle theta when the block is at pure shear, right? So suppose our block is in pure shear. When we say pure shear, that no tensile or compressive or normal stresses acting on this material at a certain plane, at our main plane. These are the outer planes on which we are applying stresses, right? So suppose we have applied this stress, we have applied the stress sigma tau, and you know that to this applied shear stresses there are complementary shear stresses which are making a if it is clockwise couple, then they are a complementary shear stresses will make anti-clockwise couple, right? And this block is in pure shear, right? And suppose let us name it A, B, C and D. Now our aim is to find out shear stresses or tensile stresses or whatever stresses, normal or shear, at an angle theta on certain inclined plane at certain angle theta. What are the stresses on this plane? This is our aim. What are the stresses on this plane? This you can see here, this plane CE. CE. What are the stresses on this plane CE? So on this plane, although we have applied shear stresses, on this plane there may be normal stresses, there may be shear stresses, right? So let us assume that normal stresses on this plane are sigma n and shear stresses on this plane are sigma t. So our aim is to find out sigma n and sigma t. This is our aim, right? So these are the stresses at an angle theta. Stresses at an angle theta to pure shear when the stress is applied is pure shear. So we want to find out the stresses at certain angle theta, and using this we will find out later on the relation between modulus of elasticity and modulus of rigidity. But first we want to do this thing, that what are sigma n and what are sigma t, and it will be useful for us, right? For the time being we want to find out this thing. So this is a triangle, suppose CEB, and I am taking this block CEB like this. CEB, this is C, this is E, and this is B. And we have applied shear stresses, pure shear. So if we want to show here, so this will be the shear stresses here, like this. This is tau, this is tau. These are the applied shear stresses, and due to this some normal stresses developed in the material at a certain angle theta, say this is angle theta, and also some shear stresses developed in the material like sigma t. T for tangential, and for normal. So to this plane CE, the tangential stresses or shear stresses are sigma t and normal stresses are sigma n. And our aim is to find out sigma n and sigma t, right? So this is our aim. Now let us make a free body diagram of this, that in which direction the stresses are developing in this block, right? So assuming that this is a point, so on this point, say this is a point and the stresses are developed in this in different directions. So we are taking, these are the right angle directions, and the sigma n is at inclined plane and sigma t is also at inclined plane. So we are making this inclined plane also. So this is our star, right? Whenever you want to solve this type of problem, make a star like this. Sigma n is in this direction. Suppose this is our main point and sigma n is in this direction, sigma n. Sigma t is inclined upward, this is sigma t. Tau vertically upward, this is tau. And this tau on EB, this is horizontal leftward, this is tau. So these are the 4 stresses at this block. A, C, B, E, there are 4 stresses, tau, sigma t and sigma n. So sigma n, sigma t, tau and tau. Now what are the angles? At what angles they are applied? The angle is theta. This angle is theta. You can see here the angle between CB and CE is theta. So this is the angle, this angle, basically this angle. This is point C, B and CE. This angle is theta. So this angle is theta. If this angle is theta, now you can easily find out the other angles on this star, right? If this angle is theta, this is 90-degree angle, this is 90 degrees, so this will be 90 minus theta. This is 90 minus theta. To this theta, this angle is also theta, opposite angles. And if this is theta and this is 90 degree, these two are 90 degrees, so this will be 90 minus theta. Again, if this angle is theta, this is 90 minus theta, this should be theta, this should be 90 minus theta, and this should be, this is theta, this is 90 minus theta, and this is theta. So one is theta, 90 minus theta, theta, 90 minus theta, theta, 90 minus theta, theta, 90 minus theta. So this will be the angle distribution in this star. So by this your question will become easy. So you will be able to find out very easily the different stresses, forces in different directions, right? So I am writing only theta so that the components can be taken easily. 90 minus theta terms I am removing. It is understood that this is 90 minus theta. Where it is not written, this is 90 minus theta. So theta 90 minus theta, theta 90 minus theta, theta 90 minus theta, and theta 90 minus theta. 90 minus theta is understood, I have removed that. Now our aim is to find out sigma n and sigma t. Now the forces are acting in different direction. This is stress. Now what we can do, we can choose any one direction, and the forces, because the body is in static equilibrium, the forces in any direction, the sum of forces in any direction will be 0, right? Because the net force should be 0, otherwise there will be acceleration in the material, and there is no acceleration in the material, only internal deformation of the material is there. So forces are in equilibrium, so net force in any direction is 0. So let us take any one direction you can choose, and sum of the forces in any one direction will be 0. So sigma f in any direction will be 0, or F net in any direction will be 0. Net force. This property we are going to use, right? So you can choose any direction. Now this is stress, these are stresses, but for equilibrium, the forces should be equal to 0, not stresses. Forces should be equal to 0. Sum of forces or net forces should be 0, right? So convert these stresses into forces. So how we can convert this stress into forces? We can assume that this block has unit dimensions, unit thickness inside the board. So there is unit thickness inside the board. Means 1 meter is the thickness inside the board. You can take it 1 meter, right? So force is stress multiplied by area. So suppose this stress tau, this stress tau in this direction multiplied by area will become the force. Area is tau EB multiplied by 1, because EB is the length and 1 is the dimensions inside the board, because this is acting on this area, EB multiplied by 1. So tau EB will be the force. Similarly, sigma n is acting on EC. So sigma n EC. So I can write sigma n EC is the force. Again, sigma T EC. Sigma T is also acting on EC. So sigma T EC. This is the force. This tau is acting on BC, vertically upward, BC. So this type vertically upward, tau BC. So tau BC. So these are the forces now. These are the forces. And multiplied by 1, everyone is multiplied by 1, because 1 is the dimensions in perpendicular direction, this board, in the direction of inside the board. So tau EB, sigma n EC, tau BC and sigma T EC are the forces acting on different planes. Now, sum of the forces in any one direction is 0. So you can take any one direction. Say I am taking this direction, sigma n direction. The reason I am taking this direction, because in sigma n direction, sigma T, the component of sigma T will be 0, because it is perpendicular to, these are perpendicular to each other. These two are perpendicular to each other. So I am taking sigma n direction once and then another sigma T direction. So I am taking 2 times the direction to find out 2 unknowns, sigma n and sigma 2. So let us take this direction as our first direction, right? So this is our direction. This direction, suppose n direction, this is our n direction, right? And this is our midpoint, say O. So this is our midpoint O, and in this direction, sigma f in n direction is equal to 0. This property we are using, because in any direction the forces, sum of forces should be equal to 0, because there is no acceleration in this material. So we are taking this direction as positive direction, and the reverse of this will be the negative direction. So sigma Fn is equal to 0. Now what are the forces acting on this direction? Sigma n EC is acting in this direction, and this is positive. Sigma n EC, sigma n into EC. Now the component of this tau EB in this direction is, because it is theta, this should be cos theta. So we can write, and this will be in the same direction. So this will be plus tau EB cos theta. Tau EB cos theta. Component of this tau, vertically upward, this tau BC, this is the force. Tau BC, and in this direction, this is 90 minus theta. So this is sin theta. When the component of force is taken 90 minus theta direction, this will be sin theta. So this is sin theta in this direction only, right? Sin theta, and this is tau BC sin theta, right? So component of this tau BC in this direction is tau BC. This is sin theta, because this is 90 minus theta angle. This theta is 90 minus theta. When we take component in this direction, this will be negative component. Is it okay? So this will be sin theta. So this will be equal to tau into BC sin theta, and that should be equal to 0. Sum of the forces in this direction should be equal to 0. So sigma n will be equal to, this will be negative minus, when we take it from the equality sign on another side, then this will become negative, this will become negative. So this will be minus tau EB, and this EC will come downward in denominator. So EB by EC cos theta plus tau BC by EC sin theta. This is negative, minus. What is EB by EC? EB by EC. In this triangle, what is EB by EC? So in this triangle, in this equation, now what is EB by EC? EB by EC perpendicular upon hypotenuse. Perpendicular upon hypotenuse is sine theta. So we will write sigma n will be equal to minus tau sine theta cos theta minus BC by EC. BC by EC. BC by EC base upon hypotenuse, that is cos theta. So minus tau cos theta sine theta. So this will become sigma n will be equal to minus tau sine theta cos theta sine theta cos theta. So this will become minus 2 tau sine theta cos theta. So sigma n will be equal to minus 2 sine theta cos theta is sine 2 theta. So minus tau sine 2 theta. So these are the normal stresses on this plane. And why this is coming negative? Because these are not tensile stresses. Basically this is compressive stresses. This is compressive stresses. That's why it is coming negative here, right? So if we are applying shear stress of this type, then the negative stress, compressive stress will be developed on CE. Normal compressive stresses will be developed. That's why this is coming negative. So these are the stresses. These are the stresses which is taking place on the inclined plane EC. But this is normal stress. We have to find out shear stress also, sigma T. How to find out this sigma T? This formula you have to remember. This formula should be remembered, minus tau sine 2 theta. In continuation, let us take another direction. Suppose this direction, shear stress direction as another direction. So this is this direction, perpendicular to this T direction, suppose, tangential direction. This tangential direction, and we are taking the components of all the forces in this direction. And then we know that because the body is in static equilibrium, so tangential force in this direction should be equal to 0. Sum of the all forces or net force in tangential direction should be equal to 0. So let us take the component of forces in tangential direction. So what are the forces acting on this direction? Sigma T is already acting in this direction. We are taking this direction as positive, and opposite to this there will be a negative direction, right? So tangential direction is sigma T into EC. This force is acting already in this tangential direction. So sigma T multiplied by EC. This is the force. Take the component of this tau BC. Tau BC has theta angle with this, so tau BC cos theta. So tau BC cos theta. Take the component of this. This is perpendicular to this, so that there is no component of this, or cos 90 is 0. So it has no component in tangential direction, because this is our normal direction, this is tangential direction. And in 90 degree there is no component of this in this direction, because these are cos 90 and cos 90 is 0. Now this component, this is opposite to this is positive direction, and we'll take a component, it will be in opposite direction, right? Opposite to this, our positive tangential direction. So this will be tau EB, and this is 90 minus theta, so this will be sine theta. So this will be minus tau EB sine theta, and this should be equal to 0, because sum of all tangential forces should be equal to 0. So sigma T will be equal to, we can take these stresses, shear stresses on another side. So you will get tau EB by this EC will come in denominator, sine theta minus tau BC by EC cos theta. And what is EB by EC? EB by EC, this is sine theta. So sigma T will be equal to tau sine theta and sine theta, this is sine square theta, minus BC by EC, this is cos theta, this is tau cos square theta. So shear stress in tangential direction, sigma T is equal to tau sin square theta minus tau cos square theta. It can be further solved that sigma T will be equal to, you can take it, minus tau cos square theta minus sin square theta, and cos square theta minus sin square theta is cos 2 theta. So sigma T will be equal to minus tau cos 2 theta. minus tau cos 2 theta. So we have obtained the result for normal stress and shear stress on a plane at certain angle theta to the pure shear. Our next topic is finding the diagonal stresses of a square block when the body is in pure shear. So diagonal stresses of a square block in pure shear. This we want to study. Diagonal stresses of a square block in pure shear. We have already read that if there is a square block, and a shear stresses of this manner, which we are saying that this is positive shear stresses and complementary shear stress will be there. So shear stresses, if there is shear stresses, then at an angle theta to this vertical plane, any vertical plane, I am taking this angle theta, say this angle theta, from the vertical plane in clockwise direction. In clockwise direction I am taking this theta, right? Suppose clockwise direction is positive direction, right? We are taking theta in this manner. This is our angle theta. What is the stress on this plane? What are the stresses? And we have already read there will be a normal stress and there will be a tangential stress. And this sigma n, we have shown that this will be equal to minus tau sine 2 theta. And this shear stress or tangential stress will be equal to minus tau cos 2 theta. This we have already read in our previous lecture. This is read already, right? Now we want to see what are the stresses on a diagonal section of a square block. Suppose now this is a square block. So suppose this is now a square block. And we want to show the stresses on this diagonal plane. So this is a square block and we have applied a pure shear like this. This is the case of pure shear. And what is the shear stresses, what is the stresses on this plane, Suppose this is, and give it a number like A, B, C and D. So what is the stresses on AC? This is what you want to see, and this angle is 45 degree. As you know that for a square block the diagonal will be at an angle 45 degree to the vertical side, right? So what will be the stresses at 45 degree? So you will see sigma n in this case will be equal to minus tau sine 2 theta, means 2 theta will become sine 90. So minus tau sine 90. So this will be, how much it will be? This will be equal to minus tau. Sine 90 is 1. So these are the normal stresses. On a plane AC, which is diagonal of this square block, right? And what is tangential stresses? That will be equal to minus tau cos 90, and cos 90 is 0. So there is no shear stress on the diagonal. There is no shear stress on diagonal, right? So how to show this? This we want to show. This and stresses we want to show on this, right? So how to show this? We will show this like this, that there are, and because this is negative, so we can say these are not tensile stresses as we have shown by this arrow. This is basically opposite to this, means compressive stresses, and magnitude is equal to tau. So these are basically compressive stresses because there is a negative sign, right? So the stresses on this plane are like this. These are compressing this block like this. these are the stresses on this block, this diagonal AC. This is sigma n, and its magnitude is equal to tau, because this is compressive. So we have removed now minus sign, because already we have changed the sign of this sigma n. So this is the stress condition, and there is no shear on this diagonal AC. This is the stress condition of this block. Now what will happen if we take a plane parallel to this AC? Parallel to this AC. If we take a plane parallel to this AC, so A, B, C, D, and this is the plane, and the stress, normal stresses, compressive stresses are there on this plane. What happen on a plane normal to parallel to this? Suppose these are two planes parallel to this. This is AC, this is suppose EF, and this is suppose GH. You can see here that this plane is also at 45 degree to the vertical. This plane is also at an angle of 45 degree to the vertical. This angle is again same, 45 degree, as like this, and also here this is also 45 degree, because these are also vertical, making 45 degree with the vertical, because these are parallel to each other. It means that on these planes also, if we put here 45 degree, we will get the same condition. Same stresses will be developing on all the parallel planes, So we can show here also that there are normal stresses, compressive in nature, acting on this plane also. Similar to this. So this is the stress condition on any plane at the diagonal or parallel to the diagonal, you can see here. In pure shear, which is if the block is in pure shear. The block is in pure shear. The block is in pure shear, and we have obtained the stresses, and that is equal to sigma n is equal to tau. As we have changed the arrow, so we can write sigma n will be equal to tau and sigma t will be equal to 0. This will be the stresses. And when we say that sigma n is equal to tau and we have shown the arrow, it means this is compressive basically. Compressive, because the sign was the negative, right? So this is the diagonal stresses on a plane AC. Similarly, we want to see the diagonal stresses on diagonal DB. What are the stresses on diagonal DB? Let us see. In continuation, let us take another diagonal BD. We have to find out the diagonal AC, the stresses on diagonal AC. Now we want to find out the stresses on diagonal BD. What will be the stresses on diagonal BD? Same block I am making again. The block is A, B, C, D, and now I want to find out what are the stresses on diagonal BD, right? And pure shear, the block is under pure shear. No tensile or compressive stresses are applied, only shear stresses are applied. But due to these applied stresses, there will be normal stresses on some diagonal, this BD, right? So what will be the stresses on the diagonal BD? Now we have taken this angle theta as clockwise positive. Now this angle, this is also 45 degree, because it is diagonal and it is a square. So on this square, this angle is 45 degree to the vertical, and this is in anti-clockwise direction. Clockwise direction we have taken positive, so anti-clockwise direction will be negative. So this 45 degree is minus 45 basically, right? and when we do sine 2 theta, this will be sine minus 90. So normal stresses will be equal to minus tau sine minus 90, and sine minus 90 is minus 1, so minus minus plus, so you will get normal stresses at tau equal to shear stress tau, and this is tensile. As we have taken the arrow, same arrow we will be used, right? Tensile stresses, because previously we have considered tensile stresses, so we have obtained the tensile stresses, so this is tensile. And sigma n is tau. What will be the shear stress? Sigma t, that will be equal to minus tau cos minus 90, and cos minus 90 is 0, so sigma t will be equal to 0. So this is the shear stresses. So we will get normal stresses only and no shear stresses on this plane BD. So you can show here, this is the tensile stresses obtained on the diagonal of this block, tensile stresses like this, and the value of these tensile stresses will be equal to tau, right? Now what will happen if we take a plane parallel to this diagonal, similar to previous case we have taken, the plane parallel to this diagonal. So again I am making the block, this block I have made A, B, C, D, and this BD is the diagonal, and I am taking planes parallel to this diagonal. There are infinite number of planes, I am taking only 2 planes, right, for reference purpose. So we have seen that this angle is anti-clockwise 45 degree. If this is anti-clockwise 45 degree, this also be anti-clockwise 45 degree, and this minus 45, this will be also negative minus 45, and this angle will also be minus 45 degree because it is also with vertical, making 45 degree in anti-clockwise direction. So if these 3 angles are same, so same condition exists here also, that sigma n will be equal to minus tau sine minus 90 for each case, whatever planes are there, infinite planes are there. So for all planes, sigma n will be equal to tau, and it is tensile, and sigma t will be equal to minus tau cos minus 90, which is equal to 0. So this means sigma t will be equal to 0. So on these planes you will get normal stresses in tensile condition. So on diagonal we have already found out, same is the condition on other planes also, right? Like this, on this also the stress will be tensile, on these planes also, all planes, whatever planes are there, infinite planes will be there, the stresses will be tensile. So this is sigma n, all are sigma n, which is equal to tau, right? So this is the condition on diagonal stresses of a square block in pure shear, and also as well as diagonal stresses we have found out the planes which are parallel to these diagonal planes, the same stresses are getting on these planes. We have found out the stresses on the diagonals of the square block. There are 2 diagonals and we have found out the stresses on these diagonals, right? Now we are combining these diagonals, right? We are combining diagonals and we want to see the condition, what is happening here. This is A, B, C and D. We have seen that the stress on AC we have already seen. Our aim is in this topic is to find out what is the strain in AC due to these diagonal stresses. So let us combine these 2 diagonals and you will get an intersection point P when we draw these 2 diagonals P. What is the stress condition on P? We want to see. What is the stress condition on, suppose here, a plane parallel to this BD, and what is the stress condition here on a point, suppose this is point Q and suppose this is point R. So there are infinite number of points like on this AC. on this AC, and there are infinite number of stress conditions are there at every point. So at every point, what is the stress condition we want to see? We seen that when we have seen that on the diagonal in AC direction, tensile stresses are there, and in BD direction compressive stresses are there. We have seen like I can make it separately. You can see here I am making this BD, this is BD, and this is AC. This diagonal is AC and this diagonal is BC. On AC, we have seen the stresses are like this, compressive, right? This type of stresses are there. And on BD, the stresses are different. They are tensile. These are compressive. On AC, the stresses are compressive. On BD, the stresses are tensile. So these are like this. Right? So on BD plane, normal stresses are there which are tensile in nature, and on this plane, AC plane, the stresses are compressive and same magnitude sigma n, which is equal to tau. So at this point, the intersection point P, if I see there are compressive strain in direction BD and compressive stresses in direction BD and tensile stresses in direction AC. So you will see if I see the stresses on this BD, on this point P, on the plane BD, you will get the point. If I see the point P will be acted upon by the tensile stresses in direction AC. In AC direction, there will be tensile stress like this. This is sigma n, and compressive stress in direction BD. So in BD direction, these are compressive stress. This is the stress condition on point P. Two stresses are there. One is tensile and one is compressive. Tensile is in the direction of AC and compressive is in the direction of BD, right? And due to these stresses, the material will get strained. AC, there will be straining in the direction AC, and because in AC direction the stresses are tensile, so it will elongate, and some lateral strain will be developed due to sigma n, and because lateral strain is compressive, this will also increase the dimensions of AC. So both strain will be positive in the direction of AC. This sigma n tensile will also increase the dimensions of AC, and this compressive sigma n in lateral direction will also increase the dimensions of AC. So you will get increased strain due to both stresses, linear stresses in direction of AC and lateral stresses, right? Same, we have seen that the stress condition is same and all the planes parallel to this. So again you will see, if I see the stress condition here at a point Q, you will see same stress condition here also, that this is tensile in this direction, AC direction, the stress is tensile, and in BD direction the stresses are compressive. Again on point R, if we see the stress condition on R, you will get the same stress condition like this. This is our point R, and there will be tensile stress in the direction of this AC and compressive stress in the direction of BD. This is our stress condition on all the points, and at all points of AC same is the stress conditions. Due to this stress condition, the strain will be developed in AC, and what is the value of that strain? So strain developed in AC will be equal to linear strain plus lateral strain. Linear strain due to this sigma n tensile, and lateral strain due to this sigma n which is compressive. So we will get linear strain sigma n upon E, which is in direction of AC, minus mu times, because sigma n is compressive in lateral direction, so it is negative. So minus sigma n upon E. So you will get strain in AC will be equal to sigma n upon E plus mu times sigma n upon E. And because we have seen that sigma n is equal to tau in magnitude. Sign convention we have already taken care here. So magnitude is sigma n is tau. So you will get strain in AC will be equal to tau upon E plus mu times tau upon E. So this is the strain in AC in terms of shear stress and Poisson's ratio. So this is a very useful equation. We will use this equation to find out relation between E and G. So remember this equation, the strain in AC, any one diagonal we have chosen, the strain in AC will be equal to tau by E plus mu times tau by E. This you have to remember. In this topic, we want to find out the strain in diagonal of a square block under pure shear. We have already find out the strain in a diagonal of the square in terms of normal stresses and Poisson's ratio, right? That you will be knowing. I am writing in the corner that result which we have already derived, that epsilon AC, the strain in diagonal came to be sigma n upon E plus mu sigma n upon E. This was the result which we have obtained in the previous lectures, and as you know that sigma n was equal to tau, so that was tau upon E plus mu tau upon E. This result you have to remember, it will be used somewhere. So I am writing in the corner these results, right? Now we want to find out strain in terms of shear strain, the strain in diagonal in terms of shear strain, right? So suppose we have a square block and the stresses are applied, shear stresses this way. The block name is ABCD. Due to shear, there will be change in dimensions of this block, and there is some change in length of this block. Say this is the length delta L which is changed in this, and this C point moves to C1, and this AC which was the original diagonal now changed to AC1. Now it becomes AC1. So AC becomes AC1, and there is change in length is delta L, right? So what is strain in AC? So strain in AC will be equal to change in length upon original length. Change in length upon original length of the diagonal AC. So epsilon AC will be equal to change in length AC1 minus AC divided by AC. This is the change in length and this is the original length. Now let us draw a perpendicular on this side. Let us draw a perpendicular on this. Suppose we draw a perpendicular here. This is a perpendicular drawn in AC1. Suppose this is C2, right? Perpendicular drawn from C to C2 on this AC1. You will see that this AC will be equal to AC2 because this is perpendicular. Is it okay? So AC will be equal to AC2. So you can write the strain in AC. Strain in AC can be written as AC1 minus AC2 divided by AC. AC1 minus AC2 divided by this AC. And what is AC1 minus AC2? That is C1 C2. So that will be equal to C1 C2 upon AC. C1 C2 upon AC. And if this is a diagonal of a square, this angle must be 45 degree. This angle must be 45 degree. In that case, if it is 90 and it is 45, this must be 45 and this must be 45. So this is a right angle triangle. So in this right angle triangle, you can see here that this C1 C2 will be equal to CC1 cos 45. CC1 cos 45, you can see here in this triangle. So C1 C2 can be written as CC1 cos 45 divided by CC1 cos 45, and this AC will be equal to this BC by cos 45 in this triangle, bigger triangle. So BC by cos 45. So this will become CC1 upon BC cos square 45. This is our strain in AC. So strain in AC is basically CC1 upon BC cos 45, cos square 45. This we have find out. Now further in this we want to proceed further. What? That this angle is a shear strain. This angle, this is our shear strain phi. And what is phi? What is phi? You have already read that phi, shear strain, will be equal to change in length upon original length. And what is change in length? CC1 upon this BC. So in this equation CC1 BC, so epsilon AC, strain in AC, will be equal to, this is CC1 by AC is phi, and this is cos square 45, this is 2, 1 by root 2 square, so this is 2. So strain in AC is basically phi by 2, right? So we have find out strain in AC two ways. This is the strain in AC in terms of shear stress and Poisson's ratio. This is a strain in AC, same diagonal AC, given by phi by 2. So we are writing here two equations for strain in AC. We are writing two equations, that strain in AC will be equal to tau by E plus mu tau by E. This is suppose equation number 1. And strain in AC is also given by shear strain by 2, half of shear strain. This is equation number 2. So these two strains we have find out for a square block under pure shear. Now we want to find out the relation between Young's modulus of elasticity and modulus of rigidity, right? So relation between Young's modulus of elasticity and modulus of rigidity. What is the relation between these two? So we will use our previous concepts, that strain in a diagonal AC, which we have already found out for a block, like this was a block which was under pure shear. This was block, and we have found out strain in this AC under pure shear, and the shear stresses were applied like this. These were the shear stresses, and strain in this diagonal AC was found out to be tau by E plus mu tau by E. This was equation number 1. Tau in strain in AC was also found out in terms of shear strain, that phi by 2. So these two equations are similar because we have found out the strain in different ways. So it means we can write phi by 2 must be equal to tau by E plus mu tau by E, because 1 is equal to 2. 1 will be equal to 2. We can get this thing, right? And what is phi? What is phi? You can go in basic again, that we have found out that shear stress is proportional to shear strain. You remember this, right? And when we remove this proportionality sign, we got a modulus of rigidity, and phi was equal to tau upon g from this equation. The shear strain must be equal to shear stress upon modulus of rigidity, right? Put this value here, so you will get, what you will get is tau by 2g must be equal to tau by E plus tau by E, mu tau by E. From here, tau is cancelled out from all these things, and you will get E will be equal to, E can be taken out common, and here E will be equal to 2g 1 plus mu. So this is the relation. This is very important relation between modulus of elasticity and modulus of rigidity. So please remember this relation.